Hello. So I'm Jyoshna Nalwala and my teammate Mudrakola Sandeep. So we are today going to present our project report, which is log likelihood estimation for LIML in stochastic frontier models. So what is the introduction to our project? So the project mainly focus on implementing the log likelihood component, which is logarithmic L1 function of the LIML estimator for stochastic frontier models with endogenous regressors. So our goal is to develop a reusable Python package to simulate synthetic data and correct for endogeneity using the control function approach and compute the log likelihood. So based on the work of Amsler and so the two main professors. So, and what is the key components of the Python package? So, our key components are data.py, which simulates synthetic data with endogeneity, generating instruments Z, endogenous regressors X, and the dependent variable Y. So, what and reduced form dot py, it performs reduced form regressions to estimate residuals, which is Ni for correcting endogeneity, and mu ci dot py computes the endogeneity correction term, which is mu ci, and conditional variance, which is sigma c square. So log likelihood dot py, which evaluates the log likelihood component, which is logarithmic L1 using the corrected model, and run dot py, which coordinates the entire pipeline, serving as the main entry point for testing and validation. So moving on, give me a second. So moving on, implementation highlights. So here we use the synthetic data generation, which simulates the data with corrected error terms to ensure endogeneity. So which enabling control testing of the LIML estimator. So and endogeneity correction. Here we uses the reduced form residuals and their correction with structural errors to compute mu CI. So log likelihood calculation, which implements the formula. We have the here, if you can see, here we have a logarithmic L1 algorithm. So for that, we are going to implement the calculation. So numerical stability safeguards are included for evaluating the normal CDF to avoid the computational issues. So what are the results and validation? So Sandeep gonna explain that.
Thank you, Joshna. So moving on to the pipeline and what exactly we have done so far is the basic introduction is pretty much cleared by my teammate. So moving on further, so what we exactly we have done here. So if you look into the code work that we have done here, basically we transform the equation that just now my teammate showed. So we transform that particular equation and made that as a package. As you can see, here is the data set sample, that's x1, x2, x3. So these components or these parameters that we have got here is basically came from the simulated synthetic data that we have taken, like from the betas and the sigma v and lambda. So our purpose is to estimate y from the given input data, which is simulated data again here. But our main motto here is to transform this particular equation and make it in a Python and later transform this Python file into a Python package. And we've done till there, and I'm going to show that in further steps too. So for now, this is what we have done in the Python. As you can see, the simulated data sample, here are the four parameters regressors, as you can see. for x1 x2, and these here we have taken two parameters as endogenous and two other are exogenous, and here is the vibe that we have transformed by the equation that we have taken or that we have shown previously. So this is the equation that we are talking about so far. So as you can see, these are the structure or the pipeline that we have followed to extract the this particular equation, and then transform that equation into Python and then into a package. So moving into the results, so we have taken for the number of observations of 500, and then the instruments is equals to k. In k is equals to 2 here, and the betas are 1.5, which is the coefficients, the 1.5, and the lambda is the 2.0 here. So after that, after the execution, the computed log likelihood function or the value for that particular log likelihood L1 is minus 967. This results confirm the successful implementation for the LIML log likelihood. So so this is what we want to show, and also we have corrected the endogeneity as mu c I, and also the endogeneity residuals are sigma c squared. So I'm going to show that in the Python too. So as you can see, so these are the first five residuals for the mu ci. These are the correction errors. So we have done that by taking the formulated we formulated by this sigma eta inverse into sigma eta, so sigma v eta. Then so then what we have done after this, so then we basically transformed that Python into a Python package. Before that we have also implemented that in the GitLab. So as you can see, we've created a log likelihood estimator as a whole package, sorry, whole GitLab repository, and then we've created a branch, new branch estimator here, and then we basically push the local GitHub Python files into the cloud, creating a new branch estimator. So here, if you can see, so this is how we've transformed the test log likelihood Python file. As you can see from here, we are simulating the data, computing mu c and log likelihood. And if I go a little bit backwards, so here is the SFF file. So this is the whole soul of the code. I would say we have taken some random sample data here, and then also computed this, and so did some set of file here to transform this into a package. So now once we are done pushing this into the GitLab, then next step we have moved into publishing this particular file into into the Python uh, Python world, I would say. So we've also published that in this particular uh, so we basically done twice. So this is one particular pip installer log likelihood estimator, and then we have done a very regular one. So there's not much big difference, but we have to do, so we had to do twice, that's it. So let me show you that in the Python 2 in the Jupyter notebook. So as you can see, so this particular is the this particular log likelihood estimator is the one of the Python package that we have implemented in Python, and this is also another one that we have done. So just it's a version difference, that's it, nothing more. But we've done this twice because just to use this for the further usage. So what's the purpose of doing in the Python for now? So this particular equation helps us, let me go to this one. So this particular equation helps us to understand the reduced form of equation in the econometrics world. So this one calculates the efficiency, and also gives you the, so as I, one moment, I'll show this. So this one gives you the efficiency metrics and also estimation parameters. There's also a reduced form of equation. This one can also be done, but we are planning to do this in a neural networks fashion. But for now, this one we have done in a Python package because we can use this multiple times rather than writing our code like 10 15 lines of code. Instead of writing all those, and we can just put it in one package and utilize multiple times. So that's the agenda of our project, or the motive of the project. So moving on to the conclusion here is that we've implemented the log likelihood component for the stochastic frontier model, as you can see, and showcase that in the Python package too. So then that's how we've done, and also push that into the GitLab. So here are some references for the for this project. Thank you.
Thank you. Yes, thank you.